Our speaker is Professor Robert Brennenberger. To tell you a bit about his background, Robert earned his PhD from Harvard University in 1983. He then moved on to do postdoctoral studies, first at University of California, Santa Barbara, and then he moved to Cambridge University, where he worked with Stephen Hawking. Then he joined the faculty at Brown University, and finally in 2004, he joined McGill University and has been a professor of physics there ever since. So we're very happy to have him speak for us tonight. Please send your warm welcomes for Robert in the chats. Robert, please take it away.
Great. You have to allow me to share the screen. Okay,
yes.
Good. Okay, can you see the full screen? Not yet. So, now it should be better. But
yeah, I can see the screen. Yeah.
Okay, now it's full screen.
Perfect. Yeah.
Okay. So I'd like to thank the organizers for giving me the chance to speak. So it's now almost 3 years that Stephen Hawking died. And I had the good fortune of being able to be a postdoc in his group for 2 years. And I got to appreciate him both as a brilliant scientist and also as a warm, caring, and outgoing person. And tonight I want to share with you some of my strong feelings about and for Hawking. So my talk will be divided into 3 parts. First, I will talk about Stephen's life. And here I won't say very much different from the things that you could discover yourselves by doing sufficient internet research. Then I'll move on to describing a little bit about his work. And again, anyone who knows about general relativity could tell you about the meaning of his works. I'm not going to tell you much original in that part. The third part will be the original part, because in the third part, I will be giving you my very personal impressions of Hawking as a person. So I want to start with this picture of Hawking, because this is the way that I remember him from my days in Cambridge. And what I want you to pay attention to is his bright eyes and his smile. These are features that were with him forever. So, Hawking was born January 1942 in Oxford. Both of his parents were Oxford University educated. His father was a medical doctor. He grew up in an intellectual household, but not a very rich household. And so Stephen went to regular schools in Oxford until 1950, and then afterwards in St. Albans, where his family moved to. So Hawking was not a stellar student, but later on in high school, in the later years, he developed a passion for science and for math. And at the wish of his father, he applied to and was accepted and entered Oxford University. And again, at the wish of his father, he joined University College, one of the Oxford colleges. He wanted to study math, but University College at the time did not offer an undergraduate degree in math. So therefore, Stephen chose the topic which was most close to math, namely physics. Now, in his first year, he was rather isolated and a bit bored. But the situation improved in his second year when he joined his college's rowing team. And here you see a picture of Stephen. I hope you can see my cursor. Can you see it, Simon?
Yeah, we can see it.
Okay. You see Hawking as cox of this college rowboat. So as a cox, he was responsible for steering the boat. And he again developed something that stayed with him throughout his life, namely his attitude as a daredevil. He took the boat on rather treacherous courses, and that led to some boat damage. But since he had joined the boat club, he also became socially more integrated, and he developed a social life. And here again, you see Stephen celebrating him. So Stephen enjoyed classical music, science fiction, and he didn't study all that hard. So when the final year, the third year of college came up, and he had to face the final exams, he sort of got nervous because he really wanted to go on and to join a PhD program at Cambridge University. And for that, he needed to get a first, which is the top degree, Cambridge. So the exams were a set of written exams, and Stephen's scores were sort of between a first and a second. And so therefore he had to take a viva, an oral exam. And so Hawking was always a bit mischievous throughout his life. And when he entered the viva room, faced his examiners asked him, "What do you want to do after graduating?" And so Stephen is reported to have said, "If you give me a first, I will go to Cambridge and become a student of the famous astronomer Fred Hoyle. But if you give me a second, I'll have to stay at Oxford, and I'm sure you don't want this to happen." And indeed, Stephen got a first. And he graduated in May 1962. It's a graduation picture. After graduating, he set off on a summer trip with a friend to Iran. And the love of travel is again something that stayed with Hawking for his entire life. Now, in October 1962, he began his PhD program in Cambridge. But again, the first year in Cambridge was not exactly such a good year. Hawking was rather depressed because, first of all, he was not assigned to Fred Hoyle, but he was assigned to Dennis Sciama as an advisor. Secondly, he wanted to study mathematical aspects of general relativity, but he realized very soon that his math background from Oxford was actually not that good. But most importantly, he was diagnosed with ALS, which is Lou Gehrig's disease, and he was given 2 years to live. So what is there to live for? So there were two things which saved Hawking. First of all, his friendship with Jane Wilde, who he had met at a party in his hometown of St. Albans. And Jane decided to stay with Hawking even after the disastrous medical diagnosis. And the second reason was the encouragement by his PhD advisor, Dennis Sciama. And here's a picture of Dennis Sciama. Now, Dennis Sciama, who at that point was much less well known than Fred Hoyle, he had the ability to get the best out of all of his students. In fact, he created the UK School of Generativity and Astrophysics, and a lot of his former students were extremely successful. So by the time of his second year, things were much better. The reputation of Stephen's brilliance started to develop. In particular, after an event where he challenged the famous Fred Hoyle, Stephen was arguing publicly in favor of the Big Bang theory, whereas Fred Hoyle was in favor of the dogma at the time, which was a steady state. And in March 1966, Stephen defended his PhD thesis. And here you see a picture of the final page of his dissertation. And you already see that his handwriting was not very legible. So things were going well. Not only did Stephen defend his thesis, but he had a job waiting for him, a research fellowship at King's College. And his PhD thesis won the Adams Prize, the prize for the best essay. He shared it with an essay by Roger Penrose. On a personal front, things were also looking better because the disease was progressing much less fast than anticipated. Stephen had gotten engaged to Jane, and in 1965 they married. And here's a picture of their wedding. You see that at that point, Stephen already had to walk with a cane. Now, Stephen and Jane had 3 children, and children were very important to Stephen. Family life was very important. And here you see a picture of Stephen and Jane with the 2 older children in front of their accommodation in Cambridge, which was given to them by the university. And you already see that at that point, Stephen was confined to a wheelchair. And well, he was a reckless cox in Oxford, and he became a reckless wheelchair driver in Cambridge. So on a professional side, things went from good to better. His fellowship was upgraded. He got a fellowship of distinction at King's College. He won first prize in an essay competition, in an international essay competition. And in 1973, he wrote a textbook in collaboration with George Ellis with the title, The Large-Scale Structure of Space-Time, where he basically summarized the work that he'd done and Penrose had done for his thesis. Now, when I mentioned this textbook to Stephen when I was a postdoc in Cambridge, Stephen chuckled and he said, "Hopefully I've learned how to write better since then." So for those of you who are not experts in general relativity, don't necessarily read this book. In 1974, Hawking got a visiting professorship at Caltech, and there a lifelong collaboration with Kip Thorne developed. When he returned to Cambridge, he became reader, Cambridge University, and at that time that meant professor. And 2 years later, he became professor, which at that point in time meant leader of the research group. And in 1979, he became Lucasian Professor of Mathematics, which is the highest, most prestigious professorship which Cambridge University offers in the sciences. It's a professorship which Newton held centuries ago. So here's a picture of Stephen in his wheelchair. So Stephen obtained many prizes for his work. He was one of the youngest to ever become Fellow of the Royal Society. He got the Eddington Medal. He got a lot of prizes, which you see listed. And I just want to point out 2 prizes. One in 2009 is the US Presidential Medal of Freedom. And in 2013, he got the Special Fundamental Physics Breakthrough Prize, which carries a $3 million award with it. And here's a picture of Stephen being awarded the US Presidential Medal of Freedom. So this is what I wanted to tell you about Stephen's life. And now I want to move on to his work. And now for a while, I'll put on my hat as a teacher. So Stephen's work focused on Einstein's theory of general relativity. And to put Stephen's work in context, I have to tell you a little bit about Einstein's theory. And there are 2 key points about Einstein's theory of general relativity. The first is that matter curves space-time. And so here's an illustration of this. This fabric represents space. Matter, here's the Earth. It curves space. It curves the fabric. And the moon, which has only a little bit of mass, it evolves in the curved space created by the Earth. So this is the first key ingredient of Einstein's theory of general relativity. The second key point is Einstein's equivalence principle, which says that in free fall, the effects of gravity are invisible. But this will not play a role in my talk, so I'll move on. Now, based on Einstein's theory, Schwarzschild showed in 1916 that it is possible to have solutions which correspond to black holes. So to illustrate a black hole, let's imagine a star slightly bigger than our sun. And this star will curve space in its vicinity. And let's take this poor star and we compress it. And as we compress it, the curvature at the boundary of the star becomes bigger and bigger. And eventually, the curvature at the boundary of the star becomes so big that nothing can escape, not even light. And this way, this star has turned into a black hole. Now, this is what Schwarzschild discovered mathematically, and he found out that at the center of this black hole, there is a singularity. Now, a singularity is a fancy word for something becoming infinite. In this case, it's some kind of curvature becoming infinite. Now, I challenge any of you who've taken a science class to make sense physically of a singularity. If you're a student and you tell your science teacher that you've measured infinity, then the teacher will rightfully laugh at you and tell you that either you've lied or else you've broken the apparatus. But Schwarzschild's solution to the equations of general relativity tell you that there's a singularity at the center of the black hole. Well, the second key prediction of Einstein's theory is that if there's matter, the universe will expand. And so to illustrate an expanding universe, let's consider a raisin bread analogy. So the analog of space is the dough in this raisin bread, and these raisins are galaxies. You stick the raisin bread in an oven, space expands, and the galaxies, even though they are fixed in the dough, they seem to move away from each other. So now this is a fancy NASA picture of how to visualize the expanding universe. So here the horizontal axis is time. Time begins here and it ends here. We are observing the universe now. According to Einstein's equations, the universe started with a singularity and then expanded and cooled down, and eventually galaxies form and we can observe lots of nice things. So more concretely, if you assume that space is the same everywhere and the same in all directions, and we have matter, that will lead to an expanding space. And Einstein tells you that a finite time into the past, we reach a point with infinite density. Again, a singularity, the Big Bang singularity. And I'm looking at the watch now. Okay. Stephen's work concerned these singularities. So let me very quickly switch to the blackboard. So if I were giving this talk in person, I would now walk to the blackboard. So I'll walk to the blackboard. Now the blackboard is a whiteboard, and I have to connect my whiteboard to the internet. And this is happening now. And now the connection is established. Okay, good. And now I want to illustrate something very simple. So let's imagine that you're taking a walk. And this is your spatial direction. You're starting here and you're going out for a walk. And this axis is going to be time. So we go for a slow walk and then we move in space as we move in time. This is our trajectory. Now you all know that light travels at a finite speed, but at a very high speed. So this is light. Okay, this is very simple. So now instead of going out for a walk on the surface of the Earth, let's assume that we are close, not too far from a black hole. So there's a black hole here. We are a safe distance from the black hole. And well, we are afraid to venture into the black hole, but we send our friend or enemy traveling towards a black hole. So the friend or enemy starts traveling, and then we watch the friend travel towards a black hole with our clock. This is our clock. And what we see is we see the friend and enemy freeze at a certain point, which is the point of no return, which is called the horizon. Okay, so this is what you see if you watch your friend move towards a black hole. Now, what does your friend see? Well, your friend's clock, distance. Well, this is the point of no return. And well, your friend is happily entering the black hole. Okay, so now the friend carries a torch and sends light out from the torch, and the light sent out from the torch will move in this direction. Now this is very bad if we go back to how we draw light normally. We draw light at a 45-degree angle. So the way that we should draw a black hole is not the way I drew it before, but this way. This is the horizon. This is the outside. This is the inside of the black hole. And at the center of the black hole, this is the center, and this is the singularity. Okay, and this is your friend's trajectory. Your friend enters a black hole and then hits the singularity. Okay, so hopefully this is all very simple. And what I illustrated is something which is called Penrose diagrams. Okay, so now I'm going to take off my hat of teacher, and I will go back to the presentation. Okay, do you see full screen?
Yeah, it's okay.
Okay, good. Good, so I'm sure all of you have heard of black holes and all of you have heard of the expanding universe. But in 1960, general relativity was considered to be a branch of applied mathematics. Physicists hadn't studied it, were not interested, had not heard of black holes, and did not know that the universe was expanding. Black hole singularities were considered to be a feature of very special solutions of some complicated equations. And Big Bang cosmology was a pejorative term. The steady state model of Hoyle was the dogma. But there was growing interest in mathematical aspects of general relativity. And Roger Penrose had just proven that black hole singularities are generic. So you take any conglomerate of stuff and you compress it. It doesn't have to be especially very symmetric. You'll get a singularity. So, and Hawking started generalizing, his thesis was to generalize Penrose's work to cosmology. Here's a picture of Hawking and Penrose. Okay, so Hawking's PhD thesis research was an extension of the singularity theorems to cosmology. So the work went very well, and Hawking produced many papers which were published in, for example, Physical Review Letters, the most prestigious journal today, or Proceedings of the Royal Society of London, which at that point was the most prestigious journal in Britain. And the work culminated in a joint paper by Penrose and Hawking establishing general singularity theorems. And here's a title page of this paper by Hawking. in Penrose, published again in Proceedings of the Royal Society of London. So this is the first body of work that Hawking is famous for. Now, this work had a substantial impact because at around the same time that Penrose and Hawking were doing this work, the microwave background radiation was discovered, and this was the death knob for the steady state theory, and it meant that standard Big Bang cosmology was correct. And standard Big Bang cosmology was developed mainly by Jim Peebles. Also, at the same time, astronomers had discovered strange objects which emitted a huge amount of radiation and which couldn't be ordinary stars or ordinary galaxies. But black holes, as something that powers these objects, was a possibility. So there was a growing interest in astronomy, cosmology, and relativity in this work. But Hawking moved on. So the second body of work for which Hawking is famous is black hole thermodynamics. Hawking was able to prove that the area of a black hole behaves in the same way as entropy. Entropy can never decrease. In the same way, the horizon area of a black hole can never decrease. So black holes very much look like thermal objects. However, the however will have to wait for 2 slides. Hawking also proved the no-hair conjecture. So that says that all black hole solutions which involve only gravity and electromagnetism are characterized by only 3 numbers: mass, charge, and angular momentum. There was early work by another Canadian, Werner Israel, but Hawking, Cart, and Robertson provided the proof. So now comes the however. So black holes seem to behave like thermal objects, but nothing can escape a black hole because they are black. So classically, black holes cannot radiate. But Hawking discovered that if you include quantum effects, then black holes can radiate. And in fact, the temperature at which they radiate is inversely proportional to the mass. And that leads to the fact that black holes evaporate faster and faster, and black holes have a finite lifetime. And the heuristic argument for this evaporation is that you have a production of particle-antiparticle pairs near the horizon. One particle falls into the black hole, and the other one has nowhere else to go than to escape. This is not the correct argument. The correct argument is in the last line, but I will move on. So now, this Hawking radiation, which I just explained, leads to a major problem, the so-called black hole information loss problem. So consider a black hole and throw a copy of the Encyclopedia Britannica, which has a lot of information, into the black hole. And you wait until the black hole has decayed by emitting Hawking radiation. So what has happened to the information? So one possibility is that the information is lost, but that goes against principles of quantum mechanics. The other possibility is that information is emitted before the black hole decays, but that means that Einstein is not completely accurate. So there was a famous bet in 1997 by Hawking and Thorne versus Preskel. So here you have Hawking, Thorne, and Preskel. Hawking and Thorne bet that Einstein is correct, quantum mechanics breaks down. Preskel bet the opposite. Well, this black hole information problem remains one of the driving forces for research in fundamental physics today. And Hawking soon realized that the problem cannot be addressed with the kind of tools that he had used so far. You needed to study the quantum mechanics of the universe in order to answer these questions. And so Hawking started a collaboration with Jim Hartle from UCSB, Jim Hartle and Hawking, where they were trying to develop a quantum mechanical picture of the entire universe. And well, they developed it, but I have limited amount of time. So their picture has some quantum resolution of the Big Bang singularity. So the universe has some strange quantum origin, and then it expands after it's classicalized. Don't ask me for details about this. This is still a little bit controversial. But anyway, after this work with Hartle, Hawking continued to do works on the forefront of fundamental physics. He worked on all of these topics, and on all of these topics, he wrote papers with more than 250 citations. Now, most theoretical physicists would be happy if they have one paper with more than 250 citations. So what I want to stress here is that Hawking remained active and working at the forefront until the very end. In fact, in 2004, he publicly conceded the bet with Prescott. So he conceded that Einstein's theory breaks down and that quantum mechanics does not break down. And here's one of the last pictures. This is a picture of his last collaboration with Andy Strominger, who's a Harvard professor, and Malcolm Perry, who's a professor in Cambridge. Okay, so this is what I wanted to tell you about Hawking's work. So now let me turn to my impressions of Hawking as a person. And I want to start with my impressions when I joined Cambridge. And I have to apologize to anyone in the audience who's either in Britain or who has been to Cambridge. But you'll see why I say the things. So I had arrived in Cambridge in October from sunny Santa Barbara. So I was a postdoc at UCSB, and UCSB is right on the beach, and I was used to swimming every day in the ocean. And there I arrive, beginning of October, in Cambridge, where the daylight starts at around 9:30 in the morning, and I say daylight because it's just dark and dreary and drizzly. And by 4:30 in the afternoon, it becomes dark again. Well, I'd found a place to live, a small room where a single bed took 2/3 of the floor space. And this room cost me 1/3 of my salary. So I was not exactly a very auspicious beginning. And this was my office building. This is the old Department of Applied Mathematics and Theoretical Physics. And this is an ugly car park. And I was sharing an office. I had a small desk in an office in the ground floor, which I shared with a graduate student and a visiting professor from Spain. Now, this car park was blocked in the evening on either side by 2 gates. And since I couldn't work in my room, and I like to work in the evenings, working in the evenings meant having to climb over the gates to escape. So this was a inauspicious beginning, and also Hawking was actually in the hospital because he just had a tracheotomy. He lost his voice, and he was recovering in the hospital. Now, he was very worried that I was going to desert Cambridge like his previous postdoc, who deserted Cambridge to join a very small, unknown startup company by the name of Microsoft. But I was never interested in doing that. I was rather interested in meeting Hawking. And Hawking wanted me to visit him in the hospital, but he'd lost his voice. So how could I communicate with him? Well, this experience was a disastrous experience, one of my most frustrating experiences ever, because the way we had to communicate was with a soundboard. I had to read where his eyes were pointing to which letter and try to guess what he wanted to say. I got more and more nervous. I did not know what he wanted to say. So this was my introduction. However, once Stephen got better and was able to return to work, everything got better. Stephen was the only staff who I knew in Cambridge who really cared for the students and who really was interacting with his group in a way that I was used to. So when Stephen recovered, he was in a wheelchair, he needed 24-hour nursing care, and he would make it into the office typically only around noon. So he would miss the typical British morning coffee. But he was always present for the afternoon tea. So at tea time, he would roll out in his wheelchair into the common room, and everyone in his group joined around the table. And we just chatted and drank tea. And what really impressed me is that Stephen was not only interested in hearing about the work of the students and the other group members, but he was really keen on talking to them about everything. So to tell you one story, one afternoon, a couple of students were talking about a movie they were going to in the evening, and suddenly Stephen's voice synthesizer started the sound saying, "Can I join in?" And so in the evening, Stephen in his wheelchair with his nurse joined the students in the movie. So Stephen by that time had become somewhat of a public figure. He was winning prizes, and sometimes he was getting money for interviews. Now, the first thing he did whenever he got a prize is to organize a party at his house. And here's a picture of one of the parties. And there's a picture of one former McGill professor in this picture, and maybe some of you can recognize this person. Also, Stephen funded Friday group lunches with the money that he won in these various prizes. And the idea of having a group lunch, this is completely common in North America, but completely uncommon, at least at that point, in Cambridge. In Cambridge, typically all students and faculty, they left around noontime, they left the department for their colleges and left the poor postdocs alone. But Stephen's Friday group lunch was a way for the group to get together. Everyone knew what the others were working on, and this created a wonderful atmosphere. Now, Stephen loved to travel, and here's a picture of him at Northeastern University giving a public talk. Here's a picture of him in Santa Barbara, again, giving a talk. Now, Stephen was not happy just traveling on the surface of the earth. He actually wanted to experience weightlessness. And indeed, a couple of years before he died, he was able to experience weightlessness. So again, it's Stephen as a daredevil. So now, Stephen had a mischievous streak. And at one point, many years after I'd left Cambridge, Stephen was co-organizer of a conference about one of the recent theoretical models about universe cosmology, which the main organizer of the conference, a colleague of Stephen's, had organized. But some of the other co-organizers had noticed, had realized that a colleague of mine and myself had found a mistake in one of the arguments of this theory. And so the co-organizers went to Stephen and said, well, shall we give Robert 15 minutes time to speak about this objection? And so Stephen turned around and said, no, he needs 30 minutes. And he greatly appreciated the controversy. Stephen remained down to earth. I'll just tell you one more story. When we were at a conference in Florence, independently, myself and him and his nurse took off an afternoon to do some tourism. And I met him and his nurse in front of a church, but there were some stairs that were needed to mount in order to get up to the entrance to the church. And so there needed to be some strong people to help lift the heavy wheelchair. And I wasn't strong enough. So the nurse went up to a couple of young Italians and asked them if they were willing to help. So they were obviously willing to help. They lifted Stephen up to the entrance of the church. And then the nurse turned around and said, asked these Italians, do you want your picture taken with Stephen? And then they chuckled and said, no, no. And so the nurse turned around to Stephen and said, well, obviously they don't know who you are. And then Stephen had a big grin in his face. So in spite of his fame, he always remained down to earth. So I want to end with one more point. Stephen was a wonderful PhD advisor. He had a large number of PhD students, and a lot of them were very successful. Gary Gibbons, one of the first students, he's professor in Cambridge. Bernard Carr, professor at Queen Mary College. Don Page, professor in Canada. Raymond Laflamme, Québécois, director of the Institute for Quantum Computation. And more recently, Simon Ross, also Québécois, who's professor at Durham University. So Stephen was able to give great projects to many or most of his students, and therefore the students were able to gain the love for the field and to succeed. So in his last years, Stephen was able to enjoy the new Department of Applied Mathematics and Theoretical Physics, which is day and night different from this old building. This is a modern complex which now houses mathematics and theoretical physics in Cambridge, a wonderful place. So Stephen was able to enjoy a few years there, but then unfortunately he died 3 years ago. And I want to leave you with this last slide. I'm just a child who has never grown up. I keep asking those how and why questions, and occasionally I find an answer. So thanks a lot.
Thank you, Robert, for a great talk. Unfortunately, you cannot hear people clapping, but I'm sure they are back at home. So we have questions. I'm going to relay them to you. The first one is a bit technical. So someone's asking, why is it surprising that the CMB, the cosmic microwave background, is extremely smooth? Isn't it expected that in the first moments after the Big Bang, the universe should be extremely low entropy?
Low entropy would mean smooth, actually. So this is a question which Stephen did not answer. And this is a question that was answered in around 1980 by a theory called inflation. But I don't want to give another talk.
Complicated subject, I understand, thank you. Someone was asking also, there was a lot of rumors and perhaps a bit of science fiction about micro black holes being created in particle collisioners, such as the LHC. And they were wondering if Stephen Hawking was worried about those or didn't care.
He was not worried about this, but he had good comments about this type of work. And unfortunately, I do not have the quotation. This is not a serious worry. Okay. And there are good reasons for that.
Okay, did Stephen play pranks on his students? Did he ever play a prank on you?
Maybe not a prank, but he assisted me in a prank. He got a lot of calls from people who had their own theories of the universe, and they wanted Hawking's opinion about that. So now obviously he could answer the phone. So he delegated to his group members to field questions, these kind of questions. Different people got assigned different countries. I actually got assigned Canada. So I got a call from someone in Toronto, and he was rather persistent. And the only way I got rid of him is to tell him that he was asking the wrong person, because Stephen did not have a Nobel Prize. He should contact Brian Josephson, who got the Nobel Prize. He's also a Cambridge professor, and he has his own crank ideas. And that got rid of this crank call. And when I told Stephen about this, he was very pleased.
It's quite the burden to have everyone look up to you for all these answers. Someone else was asking about the Nobel Prize. So Stephen Hawking did not win the Nobel Prize, maybe yet. Do you know how he felt about that?
Okay, yes, I think he felt he deserved the Nobel Prize for the importance of the work, but he realized that a direct test was lacking. Now, actually, Penrose got the Nobel Prize this past year for essentially the work that he and Hawking had done. So I think if Hawking had been alive 5 months ago, he should have been co-recipient of the Nobel Prize.
You think he should have been co-recipient of the Penrose Nobel Prize?
Yes, because the Nobel Prize really was awarded, the part of the Nobel Prize which was awarded to Penrose was for the work on singularities.
I see. Okay, black holes now. Will black holes eventually decay into to nothing over trillions of years? Will they leave some sort of imprint in the fabric of space?
That's an excellent question, and the answer is that we do not know for sure. There are different possibilities. One possibility is that there is no singularity at the center of the black hole, that there's new physics that resolves it, and string theory provides ideas for that. In this case, after the black hole has evaporated, then you won't have anything disastrous at the center. And the information that you've thrown into the black hole while it was present will be present in the universe afterwards, in some form which is hard to reconstruct. In a similar way to if you throw the Encyclopedia Britannica into a fire, into a regular fire, the book will burn up, but in principle, you could retrieve the information.
Very interesting. Another technical questions. I think we have quite a few experts watching. So if you have time, what's the correct interpretation of Hawking radiation that you alluded to when you mentioned the pair production heuristic?
Okay, so the correct interpretation is particle production in an external field. So let me do an analogy. If you have, if you take a laser, then you produce radiation from some oscillating magnetic field. So you have some background electromagnetic field, which is producing fluctuations of that field. And in a similar way, if you have a space-time which has curvature, then the fact that the space-time has curvature will lead to the production of fluctuations of the space-time. So in an expanding universe, you get these type of fluctuations. So in the early universe, you get fluctuations of space-time in the form of gravitational waves that are produced, or you get fluctuations which are coupled to matter, which are produced. And according to the inflationary universe scenario and to a couple of other early universe scenarios, everything that we see in the universe, all galaxies, originally come from something that looks like the vacuum, but fluctuations are produced in a time because the universe is expanding.
Fascinating. Thank you for that answer. Okay, back to Stephen Hawking now. You said he was very social and was interested in your personal lives as students. In terms of being a research supervisor, was he demanding?
You see, I was a postdoc and not a PhD student, so I sort of have to guess. But he gave the students good projects, but then allowed them a lot of freedom to develop these projects. In fact, the students needed to be quite self-reliant, because it was not easy to communicate with Stephen. It took a long time. So often the students were asked to seek help from other group members. For example, I assisted in guiding the PhD research of a couple of the students.
Okay. And someone is asking, after you left Cambridge, were you still in contact with him? Did you work with him?
So I didn't work with him, but I was in contact with him. And I knew that he liked to travel, and he liked giving talks, and he also liked Indian food. So when I was faculty at Brown, I had heard that he was going to get an award in Boston, and Brown University is quite close to Boston. So I invited Stephen to come and visit and give a public talk at Brown. It was around commencement time. And all that we offered Stephen, all that we promised Stephen, is a good Indian dinner. Actually, he did get an honorarium. So I definitely remained in touch with him. Whenever I visited Cambridge afterwards, I always made a point to go by and say hello to him. In fact, one of my saddest experiences was the last time that I was in Cambridge, and I was giving a talk there. I was hoping that he would be able to come to my talk, but he was so sick that he was not able to come to the talk. In fact, he was not even able to have visitors in his office.
Okay, well, it's past 8 o'clock. So just one last question that I'm curious about. That movie that Stephen Hawking was so interested in going to watch with his students, do you remember what it was?
No, because I'm not so much into movies, and I was not part of the movie.
Oh, that's unfortunate.
Sorry about that.
That's okay. Well, thank you so much for the talk. We're out of time, but thank you everyone for joining. That was a great attendance. We're very happy about that. And don't forget to register for Astro Trivia Night next Thursday, but register tonight. Thanks everyone. Thanks Robert, and have a great evening.
Thanks again for the invitation.